Today we are going to learn about implementing hierarchical clustering in Python, a step-by-step guide. We'll cover the step-by-step process of implementing hierarchical clustering using Python, equipping you with skills to perform data analysis using real datasets. Welcome to our video on implementing hierarchical clustering in Python. Hierarchical clustering is a method of cluster analysis which seeks to build a hierarchy of clusters. Unlike other clustering techniques, it doesn't require a predefined number of clusters, allowing the data to dictate the best grouping. It is particularly useful in various real-world applications such as genetic analysis, marketing segmentation, and image processing. In this video, we will explore the two main types of hierarchical clustering: agglomerative, which is a bottom-up approach, and divisive, a top-down method. We'll guide you step by step through the process of setting up your Python environment, loading datasets, processing data, and visualizing clustering results using Python's powerful libraries. By the end of this video, you will have a comprehensive understanding of how to apply hierarchical clustering to real datasets, enabling you to extract meaningful insights from complex data.
Before we dive into hierarchical clustering, it's essential to have our Python environment set up correctly. First, ensure you have Python installed on your machine. We recommend using a virtual environment to manage dependencies efficiently. You can create one using Conda. Next, install the necessary libraries: SciPy for scientific computing, NumPy for numerical operations, and Matplotlib for visualization. Use pip to install these packages with commands like pip install SciPy Matplotlib NumPy. We will also use Jupyter Notebook, an excellent tool for interactive data analysis. If you haven't installed it yet, do so using pip install JupyterLab. To ensure compatibility and avoid conflicts, check the versions of these libraries using pip list. Now, open Jupyter Notebook by typing Jupyter Notebook in your terminal. This will launch a web interface where you can create and manage your notebooks. With our environment ready, we can seamlessly proceed with implementing hierarchical clustering. Now that our environment is set up, the next step is loading and preprocessing the dataset. We will use Pandas, a powerful library for data manipulation, to load our dataset. You can import your data from a CSV file using pd.read_csv filename.csv. It's crucial to handle missing values as they can skew the clustering results. Use methods like fillNA or dropNA to manage these values effectively. Standardizing your data is another critical preprocessing step. This involves scaling the data so that each feature contributes equally to the distance calculations in clustering. Use standard scaler from scikit-learn to transform your data into a standard scale. Proper preprocessing ensures the clustering algorithm operates on a clean dataset, leading to more accurate groupings. Choose a dataset relevant to your analysis. For demonstration, we will use a sample dataset available in the scikit-learn library. By the end of this section, you should have a clean and standardized dataset ready for clustering.
Hierarchical clustering can be performed using two main algorithms: agglomerative and divisive. Agglomerative, or bottom-up clustering, starts with each data point as a separate cluster and merges them iteratively based on similarity. Divisive, or top-down clustering, begins with all data points in a single cluster, splitting them into smaller clusters. The choice between these depends on the dataset and desired outcomes. Within agglomerative clustering, various linkage criteria determine how clusters are merged. Single linkage considers the shortest distance between data points in clusters, while complete linkage uses the longest distance. Average linkage calculates the average distance between points. These criteria affect the shape and number of clusters formed. Additionally, the dendrogram is a visual tool that illustrates the arrangement of clusters. Understanding it helps in deciding the optimal number of clusters. Evaluating algorithm complexity is crucial for selecting the right algorithm, especially for large datasets. By understanding these algorithms and their applications, you can make informed decisions about which method suits your data analysis needs best. SciPy is a robust library for scientific computations, and it provides tools for performing hierarchical clustering. To start, import the necessary modules from SciPy. From scipy.cluster.hierarchy, import dendrogram, linkage. The linkage function is used to perform agglomerative clustering. It takes your data and the desired linkage criterion, for example, word, single, complete, as input. This function returns a linkage matrix, which represents the hierarchical clustering encoded as a linkage/dendrogram. Visualizing the dendrogram can help interpret the clustering results. Use the dendrogram function from SciPy to plot it. This plot will show the hierarchy of clusters and help you decide the optimal number of clusters by cutting the dendrogram at a certain height. Understanding the results involves analyzing how data points are grouped and identifying patterns or insights within the clusters. By leveraging SciPy, you can efficiently implement hierarchical clustering and interpret its results to extract valuable insights from your dataset. Visualization is a critical aspect of data analysis, enabling us to understand and interpret the clustering results effectively. Matplotlib, a popular Python library, provides tools for creating a variety of plots, including cluster visualizations. Start by importing Matplotlib. Import matplotlib.pyplot as PLT. To visualize clusters, plot your data points and use different colors to represent different clusters. This helps in distinguishing between various groups visually. You can customize your plot by adjusting the size, colors, and labels to make it more informative. Adding titles, axis labels, and legends enhances the clarity of the visualization. Consider using distinct markers or line styles for different clusters to improve readability. By interpreting visual data correctly, you can gain insights into the relationships between data points and validate the effectiveness of your clustering algorithm. Visualization not only aids in understanding clustering results but also communicates findings effectively, making it a powerful tool in data analysis. Once you have performed clustering, evaluating the results is essential to ensure the effectiveness of your analysis. Several metrics can help assess the quality of clusters. The silhouette score measures how similar an object is to its cluster compared to other clusters. A higher score indicates well-separated clusters. Inertia, or within-cluster variance, quantifies the compactness of clusters. Lower inertia suggests better-defined clusters. Comparing different clustering results involves running the algorithm with various parameters and evaluating the outcomes. This comparison helps in selecting the best clustering model for your data. Evaluation not only validates the clustering process but also guides in optimizing the algorithm for better accuracy. By understanding and applying these evaluation techniques, you can ensure that your clustering results provide meaningful and reliable insights, enhancing the overall effectiveness of your data analysis.
Parameter tuning is a crucial step in improving the accuracy of hierarchical clustering. The choice of linkage criteria, such as single, complete, or average, significantly impacts the clustering results. Each criterion offers a different perspective on cluster formation, affecting the clustering outcome. Additionally, selecting the appropriate distance metric, like Euclidean or Manhattan distance, influences how the algorithm calculates similarities between data points. Experimenting with different combinations of these parameters can lead to better clustering accuracy. Observing how parameter changes affect the results helps in understanding the algorithm's behavior and its sensitivity to different settings. By optimizing these parameters, you can enhance the performance of the clustering algorithm, ensuring more accurate and meaningful insights from your data. Parameter tuning not only improves clustering results but also provides a deeper understanding of how various factors influence the clustering process, making it an integral part of data analysis. Now, let's apply what we've learned through a hands-on example using a sample dataset. We'll use a popular dataset available in the scikit-learn library, such as the iris dataset. This dataset contains measurements of different iris flower species, ideal for demonstrating clustering. Start by importing the dataset using from sklearn.datasets import load_iris. Load the data and extract the features for clustering. Implement the hierarchical clustering using SciPy's linkage function. Choose an appropriate linkage criterion and distance metric based on our previous discussions. Once the clustering is complete, visualize the results using a dendrogram to understand the cluster hierarchy. Plot the clusters using Matplotlib, assigning different colors to each cluster for clarity. Analyze the results by comparing them with the true labels of the dataset, if available. This practical demonstration reinforces our understanding of hierarchical clustering and its application to real-world data. By replicating this example, you can build confidence in implementing hierarchical clustering on your datasets, gaining valuable insights through hands-on experience. In conclusion, hierarchical clustering is a powerful tool in data analysis, allowing for the formation of hierarchical relationships in data without predefined cluster numbers. Python's libraries, such as SciPy and Matplotlib, make implementing this technique accessible and efficient. We've covered everything from setting up your Python environment, loading and pre-processing data, to visualizing and evaluating clustering results. Remember, practice is key to mastering these skills. Apply what you've learned to different datasets to explore the diverse applications of hierarchical clustering. For further learning, consider exploring resources like online courses, tutorials, and documentation on SciPy and Matplotlib. These will deepen your understanding and enhance your data analysis capabilities. Thank you for joining us, and we hope you continue your journey in data science with confidence and curiosity.